is Colton Bailey. This is my video project 1. So my topic is linear independence. Initially, linear independence was one of the concepts that I struggled with earlier in the semester when we first learned it. Um, Linearly independent vectors are described as an indexed set v1 through vp with the property that the vector equation c1v1 plus c2v2 plus dot 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 plus cpvp equals 0 has only the trivial solution, or c1 equals dot 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 equals cp equals 0. Simply put, all constants c1 through cp are 0. So linear independence in this class, we have used linear independence a lot. We've seen it a lot in this class. Two of the highlighted modules we've seen linear independence are modules 1.7 and 2.3. This isn't limited to just those two modules. You can go back in the textbook and see that it appears in many other modules in Module 2. So Module 1.7 is linear independence, where we initially learned it, and Module 2.3 is characterizations of invertible matrices. Instances, as I said earlier, instances of linear independence are not limited to modules 1.7 and 2.3. So here is example 1 from module 1.7 in the textbook. Let v1 equal 1, 2, 3, v2 equal 4, 5, 6, and v3 equal 2, 1, 0. So we'll look at this basic example. Question A is determining if the set v1, v2, v3 is linearly independent or not. And as you can see in the solution, we must determine if there's a non-trivial solution of equation 1 above. So we reduce the augmented matrix, and we can see x1 and x2 are basic variables as they have pivots in the first two columns, and x3 is free. Each non-zero value of x3 determines a non-trivial solution of equation 1. And therefore, v1, v2, v3 are linearly dependent and obviously not linearly independent. For example 2, determine if the columns of the matrix A 0, 1, 4, 1, 2, negative 1, 5, 8, 0 are linearly independent. So we reduce the augmented matrix, and we can see that there are three basic variables. We can see that there are three pivots, therefore no free variables, and the equation AX equals 0 has only the trivial solution. Therefore, the columns of A are linearly independent. So we'll cover the invertible matrix theorem. If matrix A is invertible, the columns of A form a linearly independent set. And on the left in the purple box is a collection of all the statements that are either true or false, which make up the invertible matrix theorem. And on the right, it says the next fact follows from Theorem 8 and Exercise 10 in Section 2.2. Let A and B be square matrices. If A, B equal I, then A and B are both invertible, with B being A, the inverse of A, and A being the inverse of B. So we'll go through a basic example from Module 2.3, which says use the invertible matrix theorem to decide if A is invertible, A being the matrix 1, 0, negative 2, 3, 1, negative 2, negative 5, negative 1, 9. So we can see that A has three pivots and therefore is invertible by the invertible matrix theorem, statement C, which is A has n pivot positions, and n being, as we can see, let A be a square n by n matrix. So that would determine the size of the matrix. So we can see A is a 3 by 3 matrix, which has three pivots, and therefore satisfies statement C. And of course, if statement C is true, then all have to be true or false. Well, so in this case, all are true. And for statement E, the columns of A form a linearly independent set. So therefore, we know that matrix A is also linearly independent. And then for module 2.3, example 2, what can you say about a one-to-one linear transformation T from Rn into Rn? The solution to this is the columns of the standard matrix A of T are linearly independent by theorem 12 in section 1.9, theorem 12 being right below. So A is invertible by the invertible matrix theorem, and T maps Rn onto Rn. Also, T is invertible by theorem 9. So since we know that A is invertible by the invertible matrix theorem, we know for certain that A of T are linearly independent. And to reflect on this problem, initially linear independence was one of the concepts that was tough for me to understand, mostly because it was hard to visualize the meaning of um, being linearly independent or dependent. That was tough to visualize and sort of connect to uh, other topics we had learned previously in the class. Um, I was able to overcome this struggle purely due to the amount of connections we've made with linear independence in this course. We use it a lot. We've used it in many different modules, many different questions. So that repetition of questions has helped quite a bit. And also rereading the textbook, asking questions, whether that be to Dr. Sarah or classmates, um, that has helped quite a bit. And then, of course, watching videos, whether that be the videos that Dr. Sarah makes, or videos I can find online, be it YouTube or whatever. That has helped quite a bit as well. And this struggle was valuable to me, as it forced me to find different ways to learn and understand all the concepts in this class, especially linear independence, in a more meaningful way. And it challenged me to be able to visualize this concept and learn how to be able to understand future concepts in an easier way.